This conference will now be recorded.
There we go. Thank you. Kate has already introduced us. Kate has already called the meeting to order. So I am Lance McNevin with PPI. For those who we haven't met before, this is our official PPI reminder about no audio recordings, videos, or photos during the meeting, with the exception of PPI staff, and obviously we're recording the whole thing. Antitrust guidelines, because we do have many PPI members from many companies together here today, we are required to go through this reminder that this meeting is being conducted under PPI's antitrust policy. And that means that meeting participants must observe the policy, avoid discussions of price, production, customers, or other competitively sensitive information, follow the meeting agenda, which we'll approve in a moment, and speak up to prevent any discussions that may violate PPI's policies and procedures related to antitrust. Staff or counsel must be present at PPI meetings, and as always, PPI supports free and fair competition for the industry's products.
Thank you, Lance.
This is the agenda that was sent out with the meeting invitation.
Yes, and so we're going to do, since we have a very large group today, I'm going to do our webinar version of the agenda approval. So I'm going to ask that if there, so here's the agenda, it came out in the email. I am going to ask if there's anybody that opposes the agenda. I think that's right, Lance, right, for this version of it?
I'll give a motion to approve, so.
Thank you, and I'll, then second.
Second.
Thank you. Is there any opposition or discussion, please speak up or put it in the chat.
Not hearing any.
Not hearing any, so we'll approve the agenda for today. And as I said, it was in your meeting invitation, and I can see a version of it here.
Yes, and just before, thank you very much, Kate, for walking us through that. And just before we get started, there's probably a few other comments we need to make of the guidelines of the whole presentation today. We've got probably about 65 real slides of content, and this is a really technical topic. So some of the slides have a lot of words on them. These words are taken from PPI TN53, the document that we're going to be spending a lot of time talking about. In some cases, we're actually going to read the words from TN53 to make sure everybody understands what's in that document. There's going to be a lot of other slides with graphs and tables and charts, and Gary and I are going to take turns presenting this information. It's a complicated topic, for sure. That's why we have so many people here probably. And this is our first time going through this presentation. We hope it flows well. It's been reviewed by a few people, so we really believe that it's very accurate and correct. But we also invite comments and discussion throughout it. So as we said earlier, if you have a question about something as it comes up, submit it via the chat. Kate, would it be okay if we asked you to keep an eye on the chat window? And if you see any questions that come up that are like really timely and we should address them right now, please interrupt whoever's speaking and let us know.
Okay, I can do that. Happy to help.
All right, thank you very much.
And I will make one note, maybe, oh, sorry, go ahead. I thought you were done, Lance.
Well, I was just going to say, we don't want to leave anybody in the in the dust, so to speak, if we're going too fast.
Yep. And then one thing on the agenda I will note, and just as a point of order, there was a typo in the agenda itself, where the one he sent it out, it said 2:45 for a wrap up. That's actually 3:45. So we will go from, or we are intending to go from until 4 p.m. Central Time. Correct.
And if it goes late, if afterwards people want to continue to have discussions, that's okay. I can stay, Gary can stay, so we can keep this going so everybody can get their questions answered if there are outstanding questions at the end.
Absolutely.
We don't plan to.
Well, so I think we're going to jump into the slides. I will leave you to it, gentlemen.
Thank you very much, Kate. So here's the outline of the presentation. We're going to start with a little section, kind of a preamble, a prologue, which is about PPI TN53 and the importance of thorough awareness of this topic. And that's just kind of a few slides to explain why we're doing this, why this webinar was felt to be important. This webinar was actually approved by the management committee way back early in the summer when Gary and I proposed it to the management committee that this should be a topic we offer as a webinar. So it's been in development for a while now. And then once we get through that, the first real part, item 1, is we're going to do an introduction to chlorine resistance evaluations for PEX pipe and tubing, including PPI's history involved with the development of that. And during that part, we're going to talk about the development of ASTM F2023, and before that, the development of NSF P171. For item 2, we're going to provide an explanation of ASTM F2023 testing, the extrapolation methods, and the reporting requirements. That's the test method. For item 3, we're going to discuss the requirements for PEX tubing and PEX pipe for standard operating conditions, and also the requirements for PERT tubing and for polypropylene pipe. So there's actually 4 different pipe and tubing standards we'll be talking about at that part, because PEX tubing is one standard, PEX pipe is a different standard, and there's PERT tubing, a 3rd standard, and polypropylene pipe, a 4th standard. And then the 4th part, which is probably the most interesting, is we're going to talk about calculating chlorine resistance evaluations at other temperatures and pressures, what we're going to call non-standard temperatures and pressures. So hopefully this makes sense, and we'll have a heading at the top of all the slides to let you know which part we're at. In case you get called away for a minute and you have to come back, you should be able to keep up. Gary, can I turn it over to you? Would you like to begin with the prologue here?
Sure. Thank you, Lance, and thank you everyone for joining today. And as Lance said, there's a lot of history that's went into the chlorine test methodology for PEX tubing initially, and it's kind of odd to sit here and say that I feel like I'm kind of one of the old timers on this, and Lance and several of us on the call were very involved with the evolution of the test method F2023, and PPI played a major role in the development of it. So I first think we have to as we mentioned earlier, we'll be talking a little bit about what led to the development of the standard, but moreover, TN53 is a document that was intended to help explain chlorine resistance in the beginning, specific to PEX tubing. We did revise it in 2018 to embrace the applications for pipe outside of the standard conditions, based on PEX piping tubing manufacturer recommendations, and that can be that's actually being worked on under BC. Well, that was worked on under BC 2017-05. We also added some history about 2023 in the document then. Also, the new PEX pipe standard that Lance mentioned, F2788, that was also added to this document, as well as to the F2023 standard test methodology, that is. Of course, CSA B137.5 reference was added, as we know that F876 and B137.5 are harmonized with each other. And it's important to note that the material designation code, you'll see that MD code, or MDC, that means material designation code. We'll talk about that later on in the presentation. And then also, we wanted to give this document specifically explanations about non-standard operating conditions for PEX, such as either excessive, pressures in excess of 80 psi or temperatures in excess of 140 Fahrenheit.
Gary, if I could, just one thing.
Yes, please.
Explain to everybody. We talk about PEX tubing and pipe. Just so everybody knows, when we say PEX tubing or any kind of tubing, Formally, what that means is products where the outside diameter is 1/8 of an inch larger than the nominal size. So just like with copper tubing, 1/2-inch PEX tubing, the actual outside diameter is 5/8 of an inch. So ASTM F876 is the standard for PEX tubing. If somebody within PPI is talking about pipe, we're talking about iron pipe size pipe, or DN sized metric pipe. So polypropylene could either be IPS sized or or a DN sized metric sized pipe, like 160 millimeter OD. So that's why we kind of use the terms tubing and pipe. They're not generally being used interchangeable in this presentation here today.
Yeah, but the individual product standard does outline that in great detail, though. But yeah, thanks for that, Lance. Yeah, essentially, we're going to the document consists of 8 sections as outlined here. We'll actually touch on each of these 8 sections. The first being the scope, the second one being the background and introduction to F 2023, and also the document does touch on ANSI, NSF, CSA. Standard 61 as well. We won't really touch that today at all, but the TN 53 document does make mention of that for the drinking water approvals. Also, the next section 3 is centered on test conditions of the testing methodology itself, talking about different times at temperatures with a primary focus being on 140 or 60 degrees C. Number 4 is evaluation of the results of the testing, and then the 5th section being the significance of the chlorine resistance ratings on the application and what it means, especially for operation outside of those ratings. The section 6 then talks about the effects of excessive operating conditions for the hot water piping applications, and then finally 7 is the resources for domestic potable water system design, which we won't really get into that at all today, and it does have a short summary statement at the end of the document. So next slide then.
Yeah, and in the beginning, when we were talking about this presentation, we thought we would just use the document, just kind of have TN53 in the screen and walk through it section by section. That would essentially just be reading the standard or reading the document to everybody. So that ended up feeling pretty boring. So we're going to follow the general flow of TN53, but we're going to provide a lot more insight and data and background and story to try to make this really important.
Absolutely. Well, and there is a lot of history leading up to this this particular testing methodology, and as it says here, the importance of this topic. And it's important to note that each PEX tubing has its own limits and capabilities in regard to chlorine. All PEX tubing, certainly on the market today, is not intended to be for all applications. We think of, for instance, hydronic floor heating tubing has no need to have a very significant chlorine rating, for instance, and there's other applications that might be more rigorous than what we lay out in F 2023 with temperatures in excess of 140 Fahrenheit and maybe even some chlorine conditions that are outside of the scope. I think as it says, the adoption of PEX into the more commercial, as that was achieved, the awareness of each PEX tubing pipe's capability and limits its importance for successful installations. We want to make sure it's not, it is installed in the right applications, and we want the installations to be successful. So it's important that each of us as PEX manufacturers and PEX interested parties understand what those guidelines and limitations are, and because this test method F 2023 it's actually performed both on PERT and polypropylene pipe today. we also want to extend this discussion to include those materials as much as possible today as well. There's some nice pictures here of various installations. I believe all of these are PEX, but anyway, let's head to the next slide here.
Yeah, those are all commercial installations. So what's different about commercial versus residential is in commercial, there is the chance, the possibility that we could be having higher temperatures and higher pressures than what we normally see in a residential application.
Okay. The focus of this presentation today is in fact aimed at what we've referred to as free chlorine, and this is not, we're not going to really touch so much on chloramines or chlorine dioxide today. As Lance and I talked earlier, and many of us on this call know that there's a current BCD project, BC 2020-01, that is investigating the effects of chlorine dioxide on BCD member piping materials. So that is an active project. Actually, Kate Olinger is heading up that project. Also, we do want to point out that there is a PPI statement A that discusses specifically chloramines in comparison with free chlorine when that's used in potable water. It's also a good document and one that should be used freely throughout your organizations. A lot of work went into that in testing at the time that was developed. And on that, I guess going on to that, the testing that we did do actually shows that the chloramines testing was typically less aggressive towards the PEX pipe than what free chlorine was. Certainly was no more aggressive than free chlorine. So you'll often hear us say that chlorine, free chlorine, but actually we feel that that chloramines certainly don't offer any more of a challenge to the PEX tubing than what free chlorine does. So as it says here, we felt chloramines are less aggressive than free chlorine to PEX pipe. So please refer to statement A if you have any questions on chloramines specifically. Okay, now we get to the good, the bad, and the ugly. And everything, there's a reason why things are developed, and a reason that that this topic has received so much scrutiny in the late 90s. As many of us on the call know, and there's many new people in the industry that may not know this history, but there was a piping product widely used in North America, I think started back in the 80s, mid 80s actually, called polybutylene. And that received widespread. It was used in residential plumbing applications for several, actually many years. Until it was realized at some point in time that there was failures occurring, and those failures were directly as a result of oxidation induced by chlorine being used in potable water distribution. It wasn't just unfortunately just the polybutylene tubing that had issue. It was also the polyacetal fittings that were widely used and molded for use with the polybutylene tubing that actually had quite a challenge with free chlorine. So as a result of that, and the result of many failures, there was a class action lawsuit that's on the screen here. The links at the top actually bring you to these various settlements, but all in all, you can see, I'm not going to read this word for word, but this was a major hit for the resin companies that were involved, pipe manufacturers as well. Settlements totaling nearly $1 billion. So basically the big the biggest players at the time were the Shallow Oil Company and Hoist Salinase Corporation. And I know that's not how you pronounce that, but but you understand who the manufacturers of the resin were, and there were several of. In fact, I worked for a company at the time that was manufacturing pipe and fittings. So a very painful ending to polybutylene, and I believe in 1996, does that sound right? I think 1996, polybutylene was basically withdrawn from use for potable water tubing in North America as a direct result. And there was not very much time, if I recall the story correctly. It's a little before my time, but there was not much time to transition to another plastic piping material at that time. So let's go to the next slide here.
Well, if I could, Gary, just one point.
Sure.
In the text on the left where it says the pipes have been banned in PG and Montgomery counties. So this is from the Washington Post. So those are local counties to the Post. And a lot of plastic did get banned. And that actually made it very hard for PEX to make inroads into North America because of the bad reputation they got assigned to plastic pipes because of the polybutylene failures. So, of course, nobody would ever want anything like that to happen again. That's why we're much more responsible today with all the testing we do.
Yeah, and as a result, along the way, I think the original publication. I think before 2017. I think it was reaffirmed in 17.
Yeah, this was first published in 2004, I think.
Okay, and this document PNTN 31 was written primarily to talk about the differences between, for instance, PEX and polybutylene. And as I mentioned previously on the previous slide, the POM material, the polyacetal fitting, had significant challenge to work with hot chlorinated water. And in that time, the whole the understanding of the mechanism of free chlorine and how it would attack polymers, it was not very well understood, and certainly there was no methodology, quite frankly, in the world that actually took a look at what free chlorine in distributed potable water, the effects it has on various plastic materials. So it was very important early on, before the age of the polybutylene era was over, that how can we evaluate materials for adequate stabilization, for instance, against free chlorine. So anyway, let's head to the next slide. Okay, continued.
Yeah, this is just more information from TN31, additional information. The polybutylene product standard from ASTM, which is called D3309, doesn't even exist anymore. It was withdrawn in 2010. But in case anybody ever asks you about polybutylene, yeah, there was a standard for it, and it had no requirements for chlorine resistance. So obviously now we have these requirements for PEX and the other materials.
Yeah, and all can imagine that the impact this had on the code world was very significant. So immediate scrutiny would come to any piping material that would be brought forward. I don't know that we have it in the slide here, but PEX already had an inroads primarily in hydronic floor heating applications. So the PEX standard was already well in existence before the end of the polybutylene era, but immediately manufacturers began to look at PEX as an alternate to polybutylene. But we were going to be under a much more critical eye by end users, regulatory agencies, and of course chlorine resistance being the predominant topic of the day. Okay, let's talk about introductions to the chlorine resistance evaluations. In this section, we'll discuss briefly the first development of the NSF protocol P171, followed by and parallel with at the time of that development was ASTM F2023. We'll also touch on the various work that was done at the time by JANA Laboratories into the various mechanisms of attack of the PEX tubing, and also look at how lifetimes are determined and evaluated, and then also PPI's investigation that was done actually in real world, out in the field. A team of many of our folks that are still around today with us. We're on a I call it the water scavenger hunt of PPI that we undertook to really go out and see what we could find in the field. So let's get into that, and okay. Briefly, in the late 90s, after the PB lawsuits and settlements, as I mentioned before, we recognized, certainly the industry recognized, the resin manufacturing companies certainly recognized the need for a chlorine test method to evaluate PEX tubings and really even fittings. At the time, polyphenol sulfone was being utilized even in some of the latter PB systems. Within ASTM F17, there was a task group to develop a new test method for PEX based on those experiences of PB. A name that many of us, or I should say, a few of us probably remember. I had the privilege of meeting Steve Pregan shortly before he passed. But Steve was very involved with Shell Chemical and their experiences in developing some first generation chlorine test methodologies. JANA Laboratories was formed at that same time in into the late 90s, and also NSF International began also developing a test protocol called P171 that was actually published I think 2 years prior to F2023, and it was known as NSF P171. Let's take a quick look at P171 and what made it specific. Okay. And I don't know, on your screen it's going to be, or it's small on mine as well, but I was thinking there was a slide that had more legible text, Lance. Yeah.
Sorry. Here we go.
Okay. Yeah. Okay. The requirements of P171 and what differed a little bit from F2023 that came later is that the extrapolated service lifetime was 40 years, but that was essentially after you apply a 0.5 multiplier times the extrapolated test lifetime. So in essence, without the design factor, you would have to have a extrapolated test lifetime of 80 years. The other thing that the protocol did also establish is the water quality, and I think this is on an actual slide here. Yeah, the water quality instead of, as we'll talk here in just a minute about ORP, and Lance will talk at great length about ORP. The protocol was a fixed level of chlorine at 4.3 parts per million plus or minus 0.3, and also a pH level of 6.8 plus or minus 2. And that was the test condition. I believe the water, I don't know in the beginning if they started with DI or RO water, maybe or one of the other folks can weigh in and indicate that. I believe in the beginning it wasn't necessarily RO water or DI water, but nonetheless, that's the parameters of the protocol were prescriptive from chlorine and pH.
Yeah, Gary, and one thing I'll point out on the image on the right side, which is basically page 1 of the standard, you can see there's 2 different certification marks.
Yeah, and I was thinking we had a slide on that, but yeah.
Yeah, so one certification was called CL-R for continuous recirculation, and the other one was called CL-TD, which was identified as traditional domestic.
Yeah.
Big difference meaning recirculation, meaning it's hot all the time, it never stops. And traditional domestic is like a regular house where you probably don't have continuous recirculation pumping. Your hot water pipe is only hot for, let's say, up to 6 hours a day, was the model adopted into here.
Yes, very good. All right, and further to that point, you'll probably generically hear people talking in hallways and things at various PPI meetings, and even in your own companies about CLR, CLTD, and actually one of the product standards in the case of polypropylene actually utilizes, though it's not directly attached to the NSF old protocol. I think that the terminology came across from the protocol to the polypropylene, where it does refer to the marking as a CLTD and the CLR. So you'll hear even in PEX people refer to sometimes it's a CLR material. So yeah, okay. Well, let's get into F 2023. As work continued in the late 90s to develop in the early 2000, 2001, till finally it was actually published, I believe, in fairly late 2000, if I recall. But this was done under, as we mentioned earlier, it was basically an ASTM task group that was formed. I don't know that PPI had the structure in place that we have today, but I think there was a lot of historical work at PPI even back in that era where there were task groups and discussions from what I understood. But as you see,
a lot of the work did take place at ASTM meetings. So those ASTM meetings had huge attendance, and multi-hour task group meetings were scheduled to talk about the development of this. So this was, it was before PPI got very involved in this topic.
Yeah, and there have been, as you see on the right, historical versions. Lance went back, and these are all of the historical versions. In 2008, actually had two versions. There might be more. It actually had an 08 and 08A. The only reason I know is we were looking at that today for material designation when material designations were added for UV. We are currently in the very final stages of the most recent revision to F 2023. That's project BC 2019-05. Main committee ballot just had closed not long ago, and I believe there is just one negative withstanding on that particular project. So soon we will probably have a 2023 version of F 2023.
A 2021 version.
2021 version. Yeah, sorry, I did say a little bit. Yeah, 2021 version. Maybe.
And by the way, for those who are relatively new and don't normally attend a lot of PPI meetings, we speak acronym a lot. So if you're wondering what BCD means, that means the Building and Construction Division of PPI. And when we talk about a project number like BC 2019-05, that means it's a project started within this division in the year 2019, and it was the fifth project started within that year. And Jim Pascal of Aquatherm is the chair of this project to revise ASTM F 2023.
Indeed. Okay. As we mentioned earlier, the Jana Labs did much of literally the pioneering development work for 2023. A lot of that science, from my understanding, was based off of principles that were developed inside of Shell at the time, but they carried those principles forward, and also they began taking a look at just testing for high density polyethylene used for water service, for instance. Lots of documents were developed here, as Lance pans them across the screen here. All of these documents, I think most of these documents are publicly available, many of them on our own BCD member site location. So if you do have questions about that and would like to look into some of those documents, we do have quite an archive of those collected. The photograph in the lower left is actually what one of the test stations looked like. If you wanted to get an idea of the size, if you have no idea, I would guess that somewhere around 12 to 15 feet square box, if you will, like 3 or 4 meters square. So, and you see the little rectangles in there, that would be actually sort of a little oven that the air temperature is controlled at the same temperature as the water being pumped into the test chamber where the tubing is actually on test. So if you haven't seen one of those units before at NSF or in the prior days of JANA, or even another firm, Element in Sweden, has similar units. That's kind of what it looks like. So, Lance, anything else to add to this page?
That's pretty good stuff. I mean, I think the size of those test devices, those test rigs, it's almost the size of a shipping container, which I think was convenient for moving them around when they went from Shell, who developed the very first one, up to JANA Laboratories. And on those JANA papers that were coming across the screen, if you saw the names of the authors of some of those papers, there was Dr. Ken Oliphant of JANA, Wayne Bryce of JANA, Sarah Chung, formerly of JANA, now of CSA, and Dr. Patrick Vivian, formerly of JANA, now of PPI, now my colleague and PPI technical director. So it's great that PPI now has a lot of this technical resource in-house.
Yes, absolutely. Okay, so actually 2023, first there's a test method, then you do testing, and then I think it's important to point out that you know, the actual requirements for PEX tubing, there were no requirements, hard requirements in the standard to begin with until data was generated and results could be derived. But at some point, we had to put in actual pass-fail requirements and what minimum requirements are for potable water into the F876 standard. And this was done back in 2002. I might add that I joined the PEX world in January, 1st of January on 2002. So this is kind of where I stepped into the fire, you might say, because you know, I think a lot of us on the call know that this was not an easy topic at the time. It was a very terse time in our industry, and I do want to back up and do a shout out to JANA for doing a remarkable job in working with all the manufacturers and keeping us as much as possible objective in working forward with a common goal and a common mission. And I quite frankly don't know if that would have happened in a different setting, in a different time and space, so to speak. So I carry a lot of respect for the folks that Lance just mentioned minutes ago. So back in, like I said, 2002, we added a section in F876 that this requirement was for minimum chlorine requirement of 25% of the time at the elevated temperature, 75% of the time at 23 degrees, as we referred to earlier in the P171 protocol lingo as traditional domestic. The actual underlined in red here is what was actually added to F876.
Yeah, and the way this works, the section 6.9 of F876, all of section 6 is on requirements. So section 6.9 says, here's the requirement. You must have a minimum extrapolated time to failure of 50 years when you test and evaluate in accordance with section 7.11. And then you go to section 7.11, which is the actual test requirement. And then that talks about testing it in accordance with ASTM F2023. And then the actual time to failure extrapolation is done in accordance with section 13.3 of test method F2023. And section 13.3 is the one that talked about specifically evaluate the lifetime of the pipe being exposed 25% of the time to 140 degree water and 75% of the time to 73 degree water, which is what we'd also call traditional domestic, as established in the NSF P171 protocol a couple of years earlier.
It is a major point, Lance, that one had to kind of jump around just to figure out what actually is this? So, and I think we, in F876, that obviously didn't change that way. That didn't stay that way for very long before we added more clarity directly in F876 to cover that. So, yeah, I'm just looking here. Don't think of any questions. So, on that note, as we showed earlier, many derivations of 2023 and F876 in 2008. This is when we finally decided that we needed to do what some of the other plastic piping products have done, for instance, like for high density polyethylene, where we have the PE at the time 3408. We developed a PEX material designation code to more clearly identify what it is specific about that particular tubing, because actually in F876, from the hydrostatic side, as most of us know, and it's called the last 2 digits of the designation code, are for the HDS at 73 degrees, and PEX actually offers 2 different HDSs at 73, being 630 and 800. So we had that differentiation to make. Plus, then at the time in 2008, we wanted to recognize chlorine resistance, and that's of course what we're here talking about today. And it was decided that let's leave 0, as non-tested or non-rated. The digit 1 would be what would be the minimum requirement for all potable water applications of 75% of the time at room temperature, 25% at elevated. A big debate at the time: what do we use 1, 2, 3, 4, or we recognize that we're able to extrapolate different times at temperatures. So the idea with the chlorine resistance rating is let's reserve digit 2 and reserve digit 4, knowing that there might be some middle ground between continuous, what we refer to as continuous recirculation at 140, which is the designation of 5, versus an intermediate designation of 3, where you have 50% of the time at the elevated condition, and 50% high, 50% low. So that is how we ended up with what we have to this day. So it is conceivable, though it's probably unlikely, that we go back and add digit 2, and where future possibility exists for that. But that's where we get the class 1, 3, and 5 that you hear your colleagues in the industry talking about so much. We did add a new table 2, and it clearly describes within F876 what each of these digits mean, and of course spelled it out so you didn't have to go to any other standard to figure out, okay, this is what this means, this is what that means. Digit 3 means 50% at elevated temperature. Digit 5 means 100% of the time at 140.
Yeah, and then it was just 2 years later where we added UV resistance as one of the digits for the PEX tubing material designation code, and that was added into F876 in the year 2010.
Yep.
And that's what's showing now. So the little snippet shown in the screen now is the 2010 version of F876 and the material designation code table.
So those of you keeping track of when UV came around, it was right around 2010, and a lot of that, I might add, was driven at the time by new work that was being done at AWWA concerning water service tubing applications. So that historically happened in the right at the 2010-11 time period. Okay. Go ahead, Landry.
Well, it took us a little while to catch up. We recognized around 2015 that we had to add an official definition of the PEX tubing material designation code. So that got added into the ASTM standard called F412, which is all about terminology and definitions. So that was added in 2016 to officially define what do we mean by the PEX tubing material designation code. That's what that little blue box happens there. But this question here says, what happened between 2002 and 2008? Because 2002 is when the first chlorine resistance requirements were added to F876 for the class 1, and then it took all the way to 2008 before we added the classes 3 and 5 for chlorine resistance. So 6 years later. So here's kind of a provocative question: what happened during that time? And we're going to tell you what happened during that time. And the truth is, before a lot of people in the industry were willing to add more strict requirements or more rigorous requirements for chlorine resistance, these higher categories, there was a lot of debates about the test conditions of F2023, and in particular, the minimum 825 millivolt ORP value. ORP stands for oxidative reduction potential, which is a measurement of the aggressiveness of the water. And that's what's been established in F2023. But there was a lot of people saying, well, I'm not sure if we really need water so aggressive. So a lot of work was done towards actually establishing what should that minimum ORP really be. And then, by the way, when you heard about UV resistance requirements being added to the PEX material designation code in 2010, well, all that UV stuff actually started as a PPI project as well. There was a PPI document that is no longer published called TN33, Standard UV Radiation Exposure Method for PEX tubing. That was a PPI document that then set the stage for what became ASTM F2657. It wasn't written nearly as well as an ASTM test method, so 2657 is a superior document. But the seed document for 2657 was PPI TN33, and that was done during that time frame. But the next thing we're going to talk about here is how the industry talked about this 825 millivolt number, because, like I said, a lot of people thought that it was too high and not reflective of real water quality. They said things like, you'll never find that water in real life, so why are we testing the tubing for chlorine resistance of water that doesn't really exist out there in public water? This was one of the claims. So back then, our division within PPI, which was known as the High Temperature Division, or HTD, until 2010, that's what it was known as. So this is around 2004 timeframe. We formed a chlorine task group, and most of the BCD members back then were PEX people and participated in this and signed up for it. And we spent a lot of time then defining, debating, discussing, is F2023 test conditions really fair and accurate and correct? So on this next slide, I'm going to show you some minutes from a high temperature division chlorine task group meeting in July 2004 that was put together, a whole day meeting just to focus on this topic. And this group then talked about organizing the work to resolve these disputes. So it's 3 pages of meeting minutes. This is PPI meeting minutes from way back then. Didn't have a logo or anything like that. We're more formal today. It looks like the group of 16 of us met at a Detroit Metro Airport Hotel, a Courtyard Hotel near Ann Arbor in Romulus, Michigan. And there's some names there you'll probably recognize. Ada Chichanowski from NSF was there. Chris Haldeman, Rich Houle, Nazrin Kashefi, Randy Knapp. Now at PPI, I was there. Gary Morgan was there. Camille Rubez of PPI was running the show back then. Gary Runyon was there. Steve Sandstrom was there. And we spent all this time talking about how do we really break up F2023 to analyze it to see if it's fair and accurate. So one group said, let's focus on studying water temperature. So a group of people said, we're going to study water temperature to find out if 140 degrees is really a fair temperature to use. One group was assigned to focus on water quality requirements, and that has to do with the pH in the chlorine. One group assigned or volunteered to say, let's make a whole new test method. Let's just leave F2023 behind and talk about something completely different. Well, that work never happened, but the task group was formed to talk about it. And then there was also task group D talking about the end use recommendation. And they focused on some other research things, but really most of the effort was on temperature and water quality, and of those two, most of the time was on water quality. So the next meeting of this group was in January 2005. And I forget where we met at that time. It might have been down in Kansas City or something like that. And at this point, we had agreed that we wanted to study real world water quality. That means we wanted to go to the water treatment plants that were making the most aggressive water and actually measure that water with our own instruments to see what the pH and the chlorine and the ORP really were. So it was agreed that PPI would hire a firm called PACE Analytical that was in the business of water quality testing, and we would identify the 30 most aggressive water treatment plants, meaning the 30 areas with the most aggressive water, and we'd pay them to actually go test the water and report back. So these are the meeting minutes from January 2005, where we agreed to that plan and how they would do the testing. And we talked about what we would do with the values that they would come back to us in terms of would we pick the average value, the median value, all this kinds of stuff was well planned out. And if you're wondering, where did we find those areas with the 30 most aggressive water quality water treatment plants across the United States, there was a recent report that had been published called AWWA Water Stats. And we actually had help from Jana to take that thousands of data points from that report from AWWA and massage the data, sift through the data really to try to identify exactly what we were looking for, because we didn't care about turbidity and total dissolved solids and all this other stuff. We just cared about pH, chlorine, and what would the ORP be. So Jana helped us put together the list of what should be the most aggressive water treatment plants. This is a close-up of that table. There was more pages and pages of this, but this is just kind of the top part so that we can read it. And this is the type of data that was being reported by the water treatment plants themselves to the EPA. And then from this data, you could calculate what the ORP should be. And we just sorted by highest possible ORP. And that's where we sent PACE out to go to test the water quality. So it took them a couple of months. They reported back to us. And when the data come back, there was more debate. Some people didn't agree with the data. They didn't like the data, or they weren't sure if the data was really measured correctly, because measuring pH and chlorine, it's pretty easy with a handheld electronic instrument. Measuring ORP, it's kind of tricky because you have to keep it moving slightly in the water, but not too fast and not too slow. It has to be just right with just the right type of instruments. So there was really some legitimate debate about whether that data from PACE Analytical was accurate or not. So not everybody was happy with it. So to resolve that debate, then PPI organized what we call the ORP tour, and we picked the worst of the worst, the areas from the PACE trip that were the most aggressive, and a group of volunteers agreed to go and spend a week traveling through the Southeast US, which is actually where the biggest cluster of aggressive water happened to be located, and bring our own instruments, meaning people from different companies brought their own instruments, and we would go test the water ourselves. And also we would bring the gentleman from PACE Analytical back with us again, and also pay to have somebody from Jana Laboratories come with us to act as a referee to make sure everybody was using the instruments correctly, and then also to take Jana's own measurements. So I've got some pictures of that. This was early in the days of digital cameras, so I was enamored with that, and I took lots of pictures. PPI through Camille Rubez. Camille Rubez was PPI's director of engineering for our division back then, and he actually organized with these water treatment plants that us group of pipe geeks could come and tour their plants and go into their test rooms and actually test their water quality. So I don't know if we'd get that kind of access today, but we went into these plants ourselves and we tested the water just before it entered the distribution system, before it went to the first customer. Here's an early morning picture, people getting ready. You can see the sun is coming up. From the left, we have the gentleman from PACE unloading the van, Tracy Presnell in the first blue shirt. To his right, Camille Rubez, and to his right, Rich Houle. I invented the selfie on this day. Long before cell phones, I thought this was pretty cool, taking my own selfie. So I was there as the photographer. Here's our group again in one of these treatment plants. You can see the fellow with a notepad writing down all the numbers. That's Patrick Vivian. and now with PPI, so glad he's on board. Here's in one of the labs where we're actually collecting our own bottles of water to do our own measurements. And then in some cases, people would take our own meters and set them up side by side in the same bottle of water and compare what kinds of measurements we were getting and things like that, because this isn't necessarily a perfectly exact science. But all these taps here is how the water treatment plant tested their own water for pH and chlorine and the things they would test for. Again, here's another group of us in one of the water treatment plant labs. Again, Patrick is writing notes, taking down values of what we were measuring. And then here's one of the sheets of notes for the values that we were collecting. And at the end of all that, we entered all our values into a spreadsheet, as you can see here. So this is a table, and we really focused on 6 locations: Nashville, Madison, Hendersonville, Somerset, Kentucky, Corbin, Kentucky, and Johnson City, Tennessee. That's where we found some of the most aggressive water in the country. And you can see who was doing the measuring. I was with Rahal back then, so the first column is the Rahal measurements, then the Vanguard measurements, the PACE measurements, and then the water treatment plant's own measurements of pH and sometimes chlorine. And then we would take all those values and average them out. Some other data here. And down at the bottom of this table, it says the average of the top 5 ORP values was 790 millivolts, and the median of the top 5 ORP values was 786 millivolts. Very, very close.
Lance, I might interject here. Recently, in end of middle of September, I was in Nashville riding bikes, and I can attest that from taking a shower there that they still are fairly aggressive with the chlorine, I think. But I had forgot, honestly, till this slide came up, I had forgot that Nashville was a pretty hot location when it came to surprisingly to me was the pH. And there's reasons to question why, and maybe that's hopefully changed since then, but it was a low pH value. I mean, a relatively low pH value for potable water.
Yeah, because the low pHs below 7.5 end up being aggressive to metal pipes. So most water utility plants want their pHs, I think, above 7.5, even above 7.8, to be less aggressive to iron pipes and metal valves and fire hydrants and things like that. But yeah, we measured 6.7, 6.8 with 2.6 parts per million of chlorine in the water there, which was pretty high.
Yeah. There might be a rumor too that Lance McNevin, when he goes to Nashville here in early part of December for a groundwater ICSPA, association meeting, that he might have some of these instruments in his back pocket too. So
I don't travel with them anymore. So this was 2005. We're spending a lot of time in history here. This was 16 years ago, I guess. But in the end, we had a big meeting analyzing these results. And here's what happened. Somebody made a motion, but with the initials GM, that there is no compelling data to reduce the minimum ORP from 825 millivolts to anything lower within ASTM F2023. And that motion passed by a vote of 15-5. So there was 20 people voting. And that's how we resolved the fact that 825 really does seem like the right number. It's a little more aggressive than what we really found for real, but it's better to be a little higher than a little bit lower. And then we also agreed to form a task group to develop a continuous recirculation model in F2023 that would consider ORP decay over time. So we formed a huge task group, as you can see here. And then we actually contracted with Jana Laboratories to build some test equipment in their lab to actually measure ORP decay over time. So in other words, if you fill a hot water tank with highly chlorinated water and then heat up that water, is the ORP the same after 24 hours? And the truth is it does decay, but the results of that indicated, again, it didn't decay fast enough that anybody felt it was justified to change the 825 millivolt in F2023. So we have that data in the PPI file, but we didn't use that data to change anything in the standards. So the consensus of all this was to not reduce the minimum ORP to less than 825. And as it says here, this was followed by a very productive era within our division after that. Right after this, when we stopped fighting in the chlorine, we started work on the PEX plumbing design guide, which was published 2006. We developed the ASTM UV test method. We did other experiments with NEHB Research Center on pressure loss through plumbing systems. And then we finally agreed to add those chlorine categories 3 and 5 to ASTM F876. And that happened in 2008. So that's a lot of history. Probably spent more time on that than we should have, but hopefully people found that a little bit interesting. And we included all this just so you know there really is a really strong basis for the water quality settings that are in F2023 today.
Thank you, Lance, for walking through that. I know that you know your personal involvement with that just made it smoother coming from you, and certainly appreciate all the insights that even those of us that were involved at the time kind of forget about, that this was done, and we should feel very confident about where we stand today in that regard of the water quality. Okay, let's go into section 2. We'll discuss the 2023 water quality testing evaluations and also get into the extrapolations at the end use conditions and how that's reported. Okay, first of all, I'm just going to read the scope of 2023. This test method describes the general requirements for evaluating long-term oxidative resistance of cross-linked polyethylene PEX pipe or tubing in hot chlorinated water. The pipe or tubing used in such a testing is produced in accordance with specifications such as ASTM standard specification F876 or specification 2788 or 2788M. This test method outlines the requirements of pressurized flow-through test system, typical test pressures, also test fluid characteristics, failure type, which we'll briefly visit, and finally the data analysis. This whole method, unlike hydrostatic testing, where we are purposely generating a ductile failure over time to then be able to, in essence, use regression lines to calculate out what the ultimate lifetime of the pipe would be. This utilizes a methodology that kind of combines a couple characteristics of hydrostatic in that we do care about the hydrostatic, the stress on the wall of the pipe, but principally we're looking for a specific oxidative attack of the pipe wall itself induced by hot chlorinated water. And the diagram on the right is actually kind of discussing the different types of failure. The first one being simply a ductile failure. You'd see just a bubble forming. Finally, the little bubble gives up a burst, and that's a lot what a burst test, a quick burst, or even a long-term hydrostatic test would end up looking like. Stage 2 failure is now the pipe is thermally, it's a little more degraded, and this would be typically referred to as a stage 2 or sort of a mixed mode failure. It's not really fully oxidative failure, but yet, as you can see, there's no ductile appearance, or very little. There might be a little bit of ductile appearance around such a brittle slit, but finally, the stage 3 is, just really it does resemble a little bit, maybe not quite as drastic as the photo illustrates there, but sort of a piece of Swiss cheese without round holes, but only has the little cracks in them. But the middle set of pictures I would draw your attention to. This is typically what, if you would cut a PEX pipe apart at the end of or during the testing, here's kind of what you would see, and the bottom picture being where the obvious oxidative layer and visible cracks may only be 20 to 30% of the wall thickness, but at that point in time, there's usually a crack that propagates all the way out and results in a failure. But that's typically what you would see blown up many times, as what's in photograph the 1.C at failure. This is what the actual inner surface of the pipe would look like.
Yeah, and these figures are actually taken from a JANA report from about 15 or so years ago called Assessing Material Performance in Chlorinated Potable Water Applications. And if anybody wants a copy of that, just email it me and I can share that with you.
Okay, now we're talking from, again, section, if you have TN53, this is section 3. This covers the fact that of the ORP, which we just spent a great amount of time on talking about, being the ORP is, combination primarily between the resultant pH with the free chlorine available. The third-party labs typically use, I think the standard requires reverse osmosis or purified water, so we're not allowing any mineral content in the water, or anything else that would perhaps influence in one way or the other the oxidative attack of the tubing. This test water does represent what we feel, based on real life measurements, very, very rigorous, very, very severe conditions that don't exist in the vast majority of our markets today. But it is possible, however, that there would be more aggressive water. But I would just put a side note in on that many studies have shown in the AO world that when you get above an ORP of 840, 850, even though you could increase it maybe to 900, the speed at which the oxidative attack happens just really doesn't increase that much. It's almost like the chemical reaction can only happen so fast. So 825, that's minimum by the standard. Typically, the values probably tested or closer to 840. And as Lance mentioned previously, when the water is heated, it is typical that you see a fairly rapid decay in the ORP just from the water heating apparatus itself. This is a graph that is in the back of 2023. This actually kind of pictorially, graphically represents the effect of pH and the free chlorine content. If you look at the right side, that'd be 10 parts per million, going down to and across the bottom to as little as 0.1 part per million. And you can see that really, if you go up the ORP chart and you pick 800 and you find a line and come down, you see that you can generate, you can generate a relatively high ORP with a very small concentration of chlorine, but it does require that the pH is what I refer to as left of center, kind of that 7.2 to 7.4 pH range. That if you stay to the right side of that, typically you have to get into some pretty high concentration, which is 1.5 to 2 parts per million, to be able to generate 840 or 825 ORP.
Yeah, and Gary, kind of an
Offline, if
interesting.
anyone wants.
I'm sorry.
Go ahead, Lance.
Well, I was just going to say an interesting side note about this graph. It's been in F 2023 pretty much since the beginning. And Jim Pascal is doing a project we'll talk about later to develop a new chlorine test method for polypropylene pipes. Wanted to include the same graph in it, but wanted to know the source of the graph. Did a ton of research, and turns out that graph, as far as we can tell, was first published in 1998 in a paper by Stephen Bradley and Laurie McPherson, presented to an ANTEC conference. And Stephen Bradley, he and his dad ran a laboratory down in College Station, Texas, called MPI, and they did a lot of the early work related to chlorine in water and its aggressiveness in polybutylene way back in the mid 1990s. So we think that is the source of that graph, in case anybody was wondering.
Yeah, and I think we'll probably end up replacing through the editorial years of F 2023. That graph has got to be quite low resolution, so we'll probably put a nice, clean, crisp graph back in when that happens eventually here. So,
this is just a reference in case, like a kind of a real world reference in terms of chlorine and pH and ORPs. If you're wondering what is normal out there around the country, there is a PPI document from the municipal division called TN44, which is really about addressing the chlorine resistance of polyethylene water mains made to AWWAC 906, and it also has some reference points of average disinfectants for chlorine and average pH and the resulting ORP for some major water utilities around the country. And in this case, you'll see the ORPs that they measured was 650, 740, 750, much lower than theoretically possible.
And notice the corresponding pH, because the pH values are quite high. So, and like Kansas, I see the California Utility 1 chloramine. This would be very, very similar to our water here in Kansas City. I haven't measured ORP, but we typically always reside right around 9.2 pH, which is not fun if you have a hot tub like me and have to get the chemistry under control. It's a battle. But anyway, it is quite amazing the impact the pH has on ORP. But great paper. Yeah, so then we get in actually the test conditions, and I think most of us on the call have been involved or at some point in time with your own company's testing of PEX or PERT. But you know, typically the test temperatures are 115, 105, and 95 degrees C. There is a requirement that they be separated by 10 degrees C. There is some test data done at 90, 100, and 110 as well, but principally the test temperatures are done at three temperatures, and also two or three stress conditions depending on. But typically the pressures used are 40, 60, and 80 psig, and 80 was strategically selected, from what I understand, to represent the actual maximum residential water pressure that would be in existence. And that's let's see, yeah, and as far as the calculation, how the hoop stress is calculated, and when you hear about material stress, we're talking about the circumferential stress that exists from a result of the internal pressure on the pipe, and that calculation is in the bottom right here, where you can plug in the values, dimensions of the tubing, the DR, in the case of DR9 -1, but that's how you calculate what the actual relationship is of internal pressure to the hoop stress. Fairly straightforward calculation.
Yeah.
Roughly for a SDR9 tubing, nominally hoop stress is typically, it works out the math about 4 times what the internal test pressure is. So if you have 80 psi on the inside, typically you have 320 psi hoop stress.
Yeah, exactly. And apologies to people, we are going to be jumping back and forth a little bit between Fahrenheit and Celsius, because a lot of the standards talk about temperatures in Celsius.
And you also, we refer to a full data set for chlorine typically is a minimum of 12 data points. And these are actually generated until the point of failure, and these are entered into what we call a coefficient rate process model, excuse me, rate process method, or I've also heard of it model. We refer to it as the RPM equation. There is a separate paper discussing the rate process method, TN16, another good document to take a look at. The 3 coefficients are based on temperature in Kelvin, hoop stress is represented by S, and time in hours. So the equation is as it shows there. It's not something you simply do with a calculator. It does require a logarithmic function. And as a result, the data then can be plotted on a log graph, which we'll show here, which a lot of you have probably saw that. But this is taken from the actual JANA report titled Assessing Material Performance in Chlorinated Potable Water Applications. What is circled in red is the actual data points for each of the 3 temperature conditions of 115 C, 105, and 95 degrees C. You can see there was 3 failure points at 3 different hoop stresses. At 105, they generated, it looks like, a total of 5 points. It looks like they had 2 duplicate sets at equal hoop stress conditions. and then finally the last one being 95 degrees C at 2 different hoop stress conditions. But from that, one can, using the rate process model, one can project out in essence to the right the calculated value for down to, in what was circled here, 60 degrees C or 140 Fahrenheit. And from this, one can take the intercept of the hoop stress and bring it down to calculate what the actual years in value are. For instance, it's calculated at 80 psi internal pressure, or like I said earlier, around 320 psi hoop stress, and that generates the extrapolation for what would be a continuous end use condition of 140 Fahrenheit. This particular this is just, like I said, pulled out of a published JANA report. It's not professed to represent any one particular PEX material, but it does give a good example of what this rate process model is all about. And as the last bullet point, and we'll talk about, is we can extrapolate using various other pressures and temperatures once we have this model established. And Lance, do you want to speak to this page?
Yeah, sure. Thanks, Gary. So this is back to an excerpt from PPI TN 53 in section 3, which says, so when we talk about standard conditions, here's where we're going to define that. It says, this test procedure is designed to extrapolate the life expectancy of a hot water plumbing pipe when used at a domestic hot water temperature of 140 degrees F and a pressure of 80 psi G, gauge pressure, considered to be the normal operating limits of domestic hot water plumbing systems. Then down below it says, product standards, F876, F2788, and B137.5 require that PEX pipe and tubing intended for use in the transport of potable water have a minimum extrapolated time to failure of 50 years when tested and evaluated in accordance with F2023. So we're showing this on the screen just to kind of remind everybody that when we say the standard in-use operating condition, that is defined as 80 psi and 140 degrees. And that little image on the right-hand side from section 13.2, that's from F2023 test method under the reporting section. So you have to report the lifetime of the pipe for an internal pressure of 80 psi and at temperatures actually of 180 degrees Fahrenheit, 140 degrees Fahrenheit, and 73 degrees Fahrenheit. So the standard report actually includes 3 different temperatures in that one pressure. And then continuing on from section 4 of PPI TN 53, it says PEX pipe and tubing for drinking water applications is required, I should say are required, to have a minimum extrapolated time to failure of 50 years when tested in accordance with the test method. And then it says continuous recirculation, timed recirculation, and traditional domestic conditions are evaluated by F2023 and categorized within those standards as part of the thermoplastic pipe material designation code. Then it says see ASTM F412 for full explanation of that code. We mentioned that before. But really, we're kind of wrapping up this part of the presentation here before we go on to the next part. And the biggest lesson I think that we've established in this part over the last 15 minutes or so is that ASTM F2023, that's the test method, which includes reporting requirements, but all the actual product requirements, the pass-fail, the minimum 50 years, those are found within F876, F2788, and CSA B137.5 for PEX. And here's just a few screenshots from F2023, again, about reporting, about the different kinds of extrapolations that get reported. But always
and in the sake of time, we might want to jump ahead here just a little bit quicker, just in recognizing that. But I think part of the topic today is we wanted to talk about other temperatures and other conditions and how this methodology can be applied. The slide here, though, does show this is what's being today. Sorry, you skipped forward on me. I was just so. The pass-fail requirements are, like Len said, in the product standards themselves. So that's where you need to actually look for what the pass-fail requirements are for the various ratings and so forth. Okay,
Yeah.
so let's get into
So
the,
yeah,
the next
we've
step
got some
here.
slides. Yeah, we've got some slides with the details of exactly what all these different requirements are for PEX tubing. There's 4 standard categories. And again, this is a little bit repetitive. We've seen this before, what the 1, 3, and the 5 mean. So I think we can skip that.
Yeah.
There is a section of TN 53 that refers to those categories and how you could get a variety of material designation codes that tell you your chlorine and UV resistance, like a 1306 or a 3206. And in F876, it's section 6.9 that defines the minimum requirements. 50 years with the minimum first digit of 1 or higher, but still that's a minimum of 50 years at category 1, class 1. Within CSA B137.5, a few years ago, we did a PPI-led project to revise B137.5, the Canadian standard for PEX tubing, and basically harmonize it with F876. So now the requirements for chlorine resistance are identical, and include, in fact, B137.5 even includes the material designation code table, which is copied with permission from ASTM from F876, and clause 5.10 also spells out minimum 50 years. F2788 for PEX pipe has the exact same requirements as F876 for PEX tubing. F2769 for PERT tubing has 3 categories of performance. There is no 0 because F2769 is only for potable water. So there is no 0 chlorine resistance because you can't have that for potable water tubing. And
I think it's important to note too that PERT today doesn't have a designation code yet. Also,
true.
You know, it does. Instead of using digits, it is actually for chlorine resistance, right? This might change sometime in the future, but to Lance's point, 0 isn't there because this is intended only for potable water. So that's why. But they did mirror, if you will, from, in essence, class 1, class 3, class 5, and we can more or less say that equates to more or less the same meaning and the same values for PERT. So you'll hear maybe some referred to as PERT class 5. With, you know, the marking would literally be a CL5 on that product.
And then finally for F2389, the polypropylene pipe, it is a requirement in that standard that any pipe intended for potable water shall be labeled as either CLTD or CLR. So CLTD, that's like a class 1 for PEX. CLR, that's like a class 5 for PEX. And those are the requirements from within the ASTM F2389 for polypropylene. So it is mandatory. And by the way, we do have a PPI project led by Jim Pascal to develop a new ASTM test method to evaluate the oxidative resistance of polypropylene to hot chlorinated water. So it's a lot like F2023, but it'll be its own test method when that hopefully soon gets approved. There was 2 negatives on the last ballot, which just closed a couple of weeks ago. So we're hoping to resolve those negatives and get that published. Then we get to move on to point 4, I think, which is the most interesting part for most people, where we can actually evaluate the estimated time to failure for other operating conditions, which are above and beyond or below the specified standard end-use conditions for temperature and pressure. And the way we're going to do this, and by the way, it does say in TN 53 section 4 that you can do this, that you can do your extrapolated time to failure at other operating conditions. So that's in our document. And the way we're going to do this is use the same data set that we looked at earlier from that old Janet report and do extrapolations there. But before we do, we probably should do a quick explanation of Miner's rule. Do you think that's important, Gary?
Yes, I do. Yeah, because that is the premise for how we can do a mix of high and low temperature. There is no other way right now.
Right. So when somebody says a pipe that's traditional domestic, meaning 25% of its time, 6 hours a day, it's exposed to hot water, but the rest of the time it's exposed to 73°F water, just regular room temperature. They get those extrapolations from the same data set, but they apply this thing called Miner's rule, where they evaluate what is the lifetime for being hot all the time, what is the lifetime for being cold all the time, and then apply the hours per day to each of those conditions through this equation to then come up with a projected time to failure. And you can actually do that kind of equation for any mixture of different temperatures and different stresses. So we don't have a PPI document that describes Miner's rule. It's been around for a long time. This is just something from a website here that talks about Miner's rule that was first developed in 1945 and provides the equation. So the equation can be used for temperatures or stresses or other parts of the operating exposure.
So, and I think it's important, for manufacturers that get tough questions for maybe some commercial applications that they know very clearly that, say they're going to be operating at a higher than 140 temperature, but it might be only for 40% of the day, 25% of the day. But using Miner's equation and the original data set, you can calculate out what the expected lifetime would be at those conditions outside of what's evaluated in the final test report of F2023. Yeah.
So again, this is just a few more snippets from TN53 that says you can do evaluations at other conditions. So here's our examples we're going to walk through. And again, we're using the same data set that Jana used 15 years ago in a report. And here are our conditions we're going to evaluate. The first one is, what about 30 psi at 120 degrees? Well, that's probably not potable water unless it's actually a hydronic system using potable water, because it's very low pressure, very low temperature. But that could be something somebody would want to know the end use extrapolated time to failure of. Or what about 70 psi, which is less than 80, but 150 degrees, which is more than 140, so lower pressure, higher temperature. Or what about 90 psi at 140 degrees, so higher pressure. Or just 60 psi, lower pressure, but 165 degrees, way higher temperature. And then we're going to look at a couple of 73°F conditions, 160 psi, which is like a water service pipe, and then 200 psi, which could also be a water service pipe, but both at 73 degrees. So we're going to use this RPM equation to analyze the failure points from this particular PEX formulation to come up with the extrapolations at those various conditions. So just as a reminder, this is the data set of PEX tubing that we're evaluating that was published in this Jana report from 15 years ago. So we're not doing this for many of our members' current PEX products. This was all publicly available information. And the way we're doing it, because this is not something that you do like in the back of an envelope, like Gary said, fortunately, with Patrick Vivian as a colleague, he was able to entertain me by developing and providing me with an Excel spreadsheet that actually has the rate process model equation built in, and we can enter the failure times for our full data set at their various temperatures and pressures, and through this Excel sheet, then enter in any end use temperature or pressure and come up with the predicted test lifetime. So what I'm going to be showing you are calculations coming from this spreadsheet. It's not an official PPI publication. I can't give it to you, but that's how we're going to predict these numbers. So the way it's going to look on the screen is like this. So for that same data set, that same PEX formulation that was tested 15 years ago, at an end use condition of 80 psi and a temperature of 23 degrees C, 60 degrees C, or 82 degrees C, here are the predicted test lifetimes. Sorry, there's a typo there, test lifetimes that would come from that PEX formulation. And I'm showing the table this way just to kind of show the dramatic effect of operating temperature. So for the standard conditions, which is the yellow row in the middle, 80 psi at 60 degrees C or 140 F, This product has a predicted test lifetime of 84 years, and that's based on continuous exposure. There's no minor's rule being applied here. So that would be at the 100% hot, 24 hours a day end use condition. This product is projected to last for 84 years. If it was cold all the time, then it has a projected lifetime or predicted test lifetime of 51,000 years. So temperature has a dramatic impact there. But then if it's going to be hot, 82 degrees C is 180 F. Its predicted test lifetime drops all the way down to 3 years, from 84 to 3 by that increase in temperature. So that's just kind of a preview of what we're going to see. Here's a bigger version of that table with more temperatures added. Again, still all at 80 psi. If our temperature was just 16 C, which is 61 F, then our test lifetime is 208,000 years, which is a ridiculous number. And on the other side, if you go all the way up to 90 C, which is almost 200 F, then it drops down to 1 year. So temperature has a huge effect. So let's look at these individual exposures. Gary, you want to walk us through these individual ones?
Yeah, and yeah, I know in the sake of time here, we're starting to lose some participants. So we have just a few slides left, but just taking into account the first application of 30 psi, the low pressure application, 120 Fahrenheit. You know, for a continuous condition at that, you know, would result in a ridiculous 1,500 years of projected lifetime. This might be typical of a pressure temperature condition of a radiant heating system, but for this particular PEX application, I don't think there's any question that we would have no issue with that.
Right. And by the way, when you see a number like this, all the numbers that come from the F2023 testing don't mean that the pipe is literally going to last this long, because the temperature and the pressure may you know, degrade the pipe, and it may just fail due to pressure requirements long before this. But what this is saying, what this number is saying is, based on the math, it would take 1,508 years for oxidative attack to cause this pipe to fail. Okay, so the next one, this is a little more rigorous here.
Yeah, this is not quite at the 80 psi, but a little bit higher than the 140 Fahrenheit, and you can see that the same tubing now is down to 40 years. So you can see that the significant impact of primarily the temperature going up to 150, excuse me, yeah, 150 Fahrenheit. You know, it's still from, and then this is still based on a traditional, but excuse me, this is based on continuous, but you would then when you calculate that for traditional domestic, which I do think we have a slide on that, you know, you'll see that value increases substantially just by the reduction of the amount of time at the elevated temperature. But in this particular application for potable water, just because it is 150 Fahrenheit, you know, this would not typically be something that a PEX manufacturer would approve, and potentially this could be a misapplication. So if you know that for whatever reason they're going to be operating continuously at 150 at this pressure, probably not a good fit if they expect the kind of the minimum lifetime expectancy in years of 50.
Yeah, and if I go back a couple of slides, this is the pipe where if it was 80 psi and 60 degrees C constantly, would have a projected lifetime of 84 years. But now by increasing the temperature to 150 degrees, even at the lower pressure, we've gone from 84 years to 39 years. So a huge impact of temperature.
Yeah. And then finally, when we look at even a little bit more pressure, but yet just a little bit less temperature, you see that you know, we're well in excess of 50 years, and this would be typically probably an approved application. And for those residential applications where PRVs are controlling the curb pressure that sometimes comes in, especially neighborhoods that are hilly, quite hilly. It's not uncommon at the bottom of the hill, they're at 90 psi, and the top of the hill they're 70 or 65. So it's not uncommon that residential areas might experience 80, 90 psi, but typically higher than 90. Typically local codes are pretty stringent on making sure PRVs are installed in those applications. But this would, again, illustrates the effective temperature. Then hopping up to, again, leaving at 80 psi, but now at 160 Fahrenheit, you can see the lifetime projection substantially reduced down to 16 years. And this particular application would, again, if traditional domestic calculation would apply, would probably still be very easily over 50 years. But in a continuous recirculation, we would, I don't think anyone would recommend that.
Yeah, I don't have a slide on doing the miner's rule calculation for these examples, but it's almost 4 to 1, meaning if you're going from the continuous recirc lifetime to the traditional domestic lifetime, you can almost multiply by a factor of 4, which would be 16 times 4 equals 64 years.
Yeah, it is a good rough rule of thumb. So, okay, did we change something here? Sorry. Yeah, 165. Yeah, okay, so we reduced the pressure and we reduced the pressure to 60 psi, but still we're at the an elevated 165. And you see there too, it's not a good application if the lifetime expectancy is the 50-year benchmark. But at the same time, there might be some commercial applications where you're just looking for a certain part of the day at extremely elevated temperature, and one needs to use the miner's rule to make sure that the lifetime is what they would expect for that particular plumbing construction for that application. And then finally, at room temperature, more of a water service condition, 160 psi at 73, the calculated lifetime becomes quite conservative. And as we point out there, that I would strongly discourage anyone reporting years in thousands or even in excessive hundreds of years, but typically manufacturers will just say greater than 100 years.
Yeah.
And it is a note that that was brought to us by
Patrick.
By Patrick Vivian, that this hasn't been studied out greatly when we are talking about considerably higher stresses. So while certainly the expectation is 50 or 100 years, these years might be much over projected. And this methodology really probably doesn't accurately extrapolate at the very low temperature what the real lifetime would be of the pipe based on only cold chlorinated water. Okay, and
this one is 200 psi.
Yeah, and even increasing that a little bit further, you see that still it's well in excess of 100 years. But again, we put the disclaimer on there that that extrapolated test lifetime probably is would need to be evaluated, but certainly would be no concern. And hopefully this is one of the reasons that we have the project out to consider the 0.63 design factor, much like the PE 4710s have done for the superior slow crack growth aspects of that particular polyethylene resin, and with PEX naturally having very, very high resistance to slow crack growth. That's why some of us would very much like to see a 0.63 design factor for PEX. Okay, Lance, I'm going to let you summarize it up here and conclude.
Okay, well, we're almost done. So for the official conclusion slide, the extract from PPI TN53, this is what it says. They call it the summary within TN53. It says, thanks to the many benefits of PEX piping tubing and the associated fittings and system components, it's become common for engineers, builders, and plumbers to employ PEX potable systems for drinking water. However, for operating conditions beyond the typical domestic hot temperature of 140 degrees, and by the way, that term domestic hot also comes from NSF standard 61, and/or system pressure of 80 psi, users should contact the specific PEX pipe or tubing manufacturer to determine whether such conditions are approved for use. So if someone does contact you and say, what is the chlorine lifetime of my pipe? 60 psi and 165 degrees F. If you have your full chlorine data set, and you probably do if you're the pipe manufacturer, you could do the 3 coefficient equation yourself to do that calculation, or you could ask your certifier, whoever did the testing and the certification, if they have the Pipesen software or other software, they can probably do that calculation for you on a case-by-case basis. I'm not saying that they have to. There's no obligation for them to do it, but whoever has that data set should be able to crunch the numbers like we were doing and come up with that projection for you at various non-standard operating conditions. So let's wrap this up. We're calling this our summary and our takeaway. And hopefully everybody got this information and it makes sense. Number one, the actual end use exposure plays a big role in the estimated time to failure for each PEX material. Chloramines are less aggressive than free chlorine. Remember that from the beginning, and that makes the time to failure go up. But chlorine dioxide, based on the data that we've collected so far through the project shown here, that's more aggressive than free chlorine, and that'll probably make your estimated time to failure go down. To the next point, it says lower chlorination or a higher pH and a lower ORP value reduce the aggressiveness of the water, and therefore that should extend your pipe lifetimes, meaning the F2023 projection is probably conservative, maybe too conservative. But PPI has not published any evaluation of other water conditions, so there's no established value on what happens if my ORP is just 750 millivolts. So each manufacturer would have to make that evaluation on their own. But then for sure that we just saw that if the system is using higher temperatures and or pressures, that would definitely increase the rate of oxidative decay, and then that naturally reduces the pipe lifetimes. So green arrow going up, pipe lifetime should be extended. Red arrow going down, pipe lifetimes should be reduced. So that's kind of the simple recount of everything we've gone through. Here was the outline that we went through. We did definitely touch on all these points. We probably ran a little long and spent too much time on some of these points, so I'll apologize for that. We've never ran the seminar before. But at this point, we still do have a lot of people on, and 51 people connected. And at this point, I think we want to open it up to any questions or discussion.
Lance, there's a chat from Jonathan Simon that he put up at 4:36 about the EPA guidelines. I don't know if you saw it.
Okay. Yeah, I didn't page down. Thank you, Joe. Since 2005, the EPA guidelines for water treatment have evolved and water district service areas have gotten much larger. Has this study been repeated since 2005 to validate the 825 millivolt, and is this number still accurate?
Well, it hasn't been redone by us, but AWWA does continue to publish their water stats reports every so often, not on a super regular basis. And PPI has been paying attention to those values, not just for this topic, but also to see who is switching to possibly free chlorine. And there's not much of that out there. So I think for the data that we've seen coming out of the EPA or AWWA, there's no reason to believe that any of our values here should change. Certainly, it's not getting any more aggressive, not based on anything that I've seen. Jonathan, are you still on? I'm not sure if that answers your question.
I'm on and it does. Thank you.
All right, thank you for the question.
And Lance, do we know when the next water quality survey is due nationally?
I haven't seen that there's any kind of regular schedule for this.
Okay. Yeah, I just didn't know in the various AWWA circles and things that we are in, if anyone's heard anything.
Unfortunately, no, I haven't.
Okay.
Is there any other questions from anyone? This would be a good time if there was anything we went over too fast, or if we ever contradicted ourselves, or left something out. There's probably one thing that we didn't talk about that I could talk about, and that's when you do a lot of these extrapolations.
With
It's
pipes
not a
in.
requirement. Well, it's not a requirement in the standards to look at a 95% lower confidence level, but all the extrapolations we did are just based on average failure times. If you were testing your pipes and even at 60 PSI, 105 degrees Celsius failure time, if you had 3 samples and there was a really wide range in the failure times of those 3 samples, that would kind of indicate that you probably should be a little more conservative in your extrapolations, because some of your pipes overperform and some of them underperform and some are the average. So if in your own test data you see a lot of scatter, you probably should apply your own conservative factor, and the formal way to do that would be to do a 95% lower confidence level adjustment to your extrapolated times to failure. The little Excel file I have here doesn't do that. That was all based on average failure times.
Yeah, and those of you that do have access to pipes and software, that has a lot of features built into it, so you can, do the calculations just by plugging in the failure times.
Yeah.
Okay. Anything else, or even after the fact, if there's something that's spurned a well, hey, maybe we ought to take a look at this or that aspect of F 2023. And I know we've just completed a review of F 2023, but I do think that we always should be looking for ways to simplify and solidify, if you will, the methodology itself. So please don't hesitate to bring questions, and certainly if you think it justifies a project, we can certainly take that up amongst the management committee. I know a few of you know, but I'm currently the R&D chair for our division for the research and development projects, and we've got a lot of irons in the fire right now. Some of those are on hold, but we're working on a lot of them. But as always, if you think that there's a need, at least let us know about it.
Yeah, and one other thing I'll add, just from in the chart standpoint, we had Jonathan's question, but Kevin also shared some, pH values and other in parts of British Columbia that were extremely low. So I think the water quality around the United States and Canada continues to be of question, especially on some of these things, which when we talk about controlling, or monitoring some of these parameters, it's definitely a challenge for those water treatment facilities.
Yeah, for sure. Thanks for pointing that out, Kate. That's dramatically lower than normal.
Yep.
Yeah, don't get that in your eyes. 5.8, you'd feel it.
Yeah. Anything else? And we can.
I guess as it is a PPI meeting, we always ask for new business near the end. Robert has a question. Is there some history around Annex 1 of F 2023? Don't know, Robert. I don't have it open right now. You want to tell us what
it is? The DLT test, the 5 specimens that, how was that determined to be, or how was that validated? NSF uses the Annex A1, which basically says you test 5 specimens at the top temperatures, and if they're above or within the 95% confidence limit then of the original data set, then these data sets are considered equivalent. Just wondered if there was a bit of history that you guys had on that, since we did a lot of history.
Robert, does that actually state the highest temperature tested in the full data set, or is it one of the temperatures tested?
They do, and they actually they do 115 degrees C and 60 and 40
No, but
PSI typically.
yeah, typically that's the case, but does it actually limit? Lance is pulling it up here right now. We can take a look at it, but if there's those that have to run, I want to just thank you for your participation today. We'll continue on with this discussion, but certainly we've had a great turnout today. We had as many as 76 at one short time, mostly 75 to 72. So it's a fantastic turnout today. But yeah, let's take a look at this and see.
Yeah. Because I'm curious about the background where Annex A1 came from, because it's kind of an important part of this whole discussion about equivalencies as well, because Annex A1 is also used for the UV equivalency as well. You do
as an option, right? Yeah, five unexposed specimens compared with 5 exposed specimens, yes.
Or you can have 5 exposed specimens compared to the original data set and those kind of things. So
yeah, I do, Robert, I would make a note in A1.1.1 that I don't know exactly the year it was changed, but not long ago, but in standard 14, NSF ANSI standard 14, it doesn't say any longer highest temperature can test at one of.
Sorry, I said highest temperature. The reason people pick the highest temperature is it's fastest.
But you are right in what you said. It does remind me that at some point, we really should. We really should review, if you will, the annex here and consider, if you will, almost backwards harmonizing that, because there really shouldn't be anything that precludes a manufacturer from doing this verification or validation at one of the 3 temperatures used. Obviously, if you want to do that for many thousands of hours, you can do it the lowest temperature, but certainly the intermediate temperature, and I know we've talked about that a lot in the development of the polypropylene standard that 115C, and even for PEX, the 115C testing, while it is quicker, it might be naturally a little bit more scatter, given that the activation temperature is so much affected at 115C, or the activation energy is seemingly so impacted at 115C, and may not be a true representation, if you will, of the polymer. So anyway, yeah, we'll take a look at that. I think down the road, that's a great point that maybe didn't mean to bring that up, but I do think that honestly, sometimes I tend to think we kind of avoid looking at the annexes or the appendices when we're looking at revising a standard, but perhaps we'll take this up separately.
Yeah. Well, the thing is that this Annex A1 is actually the thing that we have day-to-day exposure to, well, more or less a year-to-year exposure to. You might, a company might develop one 12-point data set every decade or 2, and then after that, just leave it, because it's an expensive, time-consuming process. But DLT tests are done.
Yeah,
very
depending
frequent.
on, with the colors involved, yes. Mm-hmm. Yeah.
So it's like, you do a DLT, it's a new color, you do and then you have a new color, then you want to establish UV, then you do another DLT, and then so on and so on, and so
it adds up.
And then you change one small thing in your formulation, and it's like, well, okay, we should do another DLT just to make sure, and then on and on we go. So.
Yeah, no, it's a great point, Robert. It's a great point.
All right, we will dig into that deeper afterwards.
All right, thank you. Thanks for running the presentation.
Thank you.
Well,
it's early in the day for you.
All right. Well, I want to say thank you to Lance and Gary, and I hope the audience found this valuable. It sounds like it did. I think it's a very complex topic, and it's good to hear the history and how we came about as well, and the implications of it. So thank you both for taking the time to put this together. And we got up, I saw at one point we had 77, I think, attendees. Even at like, I checked about 15 minutes ago, we still had over 50 people on, even though we'd gone over a little bit. So obviously a hot topic. Thank you both for.
No pun intended.
Yeah.
A hot water topic.
Exactly. Anything else? Otherwise, I will entertain a motion to adjourn.
Well, so moved then, since my microphone's on.
Second.
All right. Thanks, everybody. Have a good afternoon. And again, thank you for all your time for putting it together and for everyone attending. Have a good
Thanks.
night.
Bye, everybody.
Bye.
Bye.
Thank
Thank you very much, Lance.
Oh, you too, Gary.
Thank you,
Great job.